Hello, class. Okay, so we're going to talk about pendulums today, which is another example of simple harmonic motion. So we're going to start out with a very simple pendulum where we're going to tie a mass to the end of a string and pull it through an angle theta and let it just swing back and forth. And say the string has a length L, we hang a mass M from the end of it, and we want to describe this motion. So basically, what we want to find mainly is theta as a function of time. So we can describe the back and forth motion of it. Now, we're going to start with Newton's second law of motion in rotational form. So torque equals I alpha. Now this is what we call a simple pendulum. It's just a mass on the end of a string. Now technically the string has some mass as well. It has a moment of inertia of its own, but that's very small compared to whatever's attached to it. Like we can hang a 1 kilogram mass on a string, and the string itself is completely insignificant. So let's apply Newton's second law, the rotational form, to this problem here. So first, say that's our axis of rotation, and we'll stick to our typical notation that counterclockwise is positive. Like say theta equals 0 is when we're hanging down vertically, and so this would be a positive angle here. So as we release it, theta is going to decrease to 0, then go to negative values. So that's our conventional form where we measure angles counterclockwise. So we have two things to look at here. One is torque, and the other is the moment of inertia. Let's start out with torque. So what forces are acting on this mass? We have gravity downwards, and we have tension. Now, the torque due to tension is 0 because this vector is pointing directly at our axis of rotation. Lever arm here is clearly going to be 0. So the torque due to tension is 0. Let's look at the torque due to gravity. So we have our line of force here, and our lever arm is a distance from the axis of rotation to that line of force. And so the torque is going to be mgl in magnitude. Now, in direction, gravity is going to cause a clockwise torque right when we release it. And so the torque is actually negative. We have a decreasing angle. So we have a negative torque here. This torque is causing the angle to decrease. So that is a negative torque. Okay. But we want to find what this lever arm is as well in terms of the variables that we know. And if this angle is theta, this angle is theta as well. And we have a right triangle here. And so we can say that the lever arm is equal to big L sine of theta. The lever arm is opposite the angle, so we use sine. So it's the hypotenuse times the sine of the angle. So I've got the torque part done. Now let's look at the moment of inertia. Well, that one's going to be easy. We have a point particle. All the mass is concentrated at the end of the string. So we ignore the mass of the string itself, and so the moment of inertia is just ml squared. So what I want to do here is let's move everything over to one side. So we move this term over here, becomes positive on the other side. We add that up and get 0. And let's divide everything by ml squared. So we divide each term by ml squared. Now 0 divided by ml squared is still going to be 0. And so what we have here is alpha. So here the m's cancel out. One of the l's cancels out. We have g over l sine of theta. So applying the rotational version of Newton's second law to this mass on a string, this is the equation that we get. Now, let's look at the units of g over l. Here we go to g as meters per second squared. Divide by meters. We get 1 over second squared. Or radians squared per second squared. And so if we take the square root, we get radians per second. So we can define, let's do this. Let's define omega squared to be g over L. And again, this is a constant. The length of the string is constant. G is obviously constant. So again, we can do this. And then the equation that we get is alpha plus omega squared sine of theta equals 0. Now, the question is, what do we do with this? We have this equation. We'd like to solve it. We want to find theta as a function of time. And let's come over here for a moment. We have position, velocity, and acceleration. So there's a relation between x and a. If we look at our angular variables, the relation between a and x is exactly the same as the relation between alpha and theta. And so, in a sense, if we had alpha plus omega squared theta equals 0, we'd have the exact same equation mathematically, which would have the exact same solution. But we don't really have that. Instead of alpha plus omega squared theta equals 0, we have alpha plus omega squared sine of theta equals 0. That's a bit of a problem. So basically, I lied to you earlier. I said that this pendulum is an example of simple harmonic motion, but actually it's not, because of this sine of theta term. But there's a way we can fix that, and that is to just replace sine of theta with theta. Now, obviously, that raises the question, can we do that? And if you look, I have a table in the notes. Maybe I'll just hold it up. So we've got theta in degrees, and then in radians, and also sine of theta. And if you start at the bottom, and we're at 90 degrees, sine of theta is 1, theta itself is 1.57 roughly. There's a pretty significant difference between theta and sine of theta. But as you go down, when you get to like 8 degrees, looks like we have 0.140, 0.139. You have to go to 3 significant figures to even notice a difference. And then for 7 degrees and less, there's no difference to 3 significant figures. And so what we're doing is we're making the small angle approximation. We say sine of theta is approximately equal to theta. And that's perfectly fine if you are, in radians and your angle is around 10 degrees or less. So when I said this is simple harmonic motion, it's extremely close to it, provided that this angle is small, like 10 degrees or less. And the larger the angle is, the farther away from simple harmonic motion we're going to get. We're still going to get oscillatory motion, but it's not going to be, just simple harmonic motion is this. So we don't have that exactly, but when this small angle approximation is valid, then we get simple harmonic motion. Now, we're going to do a lab on this where, we're going to play around with pendulums. And, we want to be able to describe the motion of it. One thing we're going to talk about next is the period of the motion. How long is it going to take to complete one cycle? And we're going to try various things. Like, we have a pendulum that depends on, there's 3 variables here. There's mass, length, and theta. And so we can do an experiment where we say, let's just change the mass. So we're going to fix an angle theta and a length of the string L and just hang different masses and see, does mass affect the period of motion? And then we can try fixing the mass and the angle that we release it from, but change the length of the string. Will that have any effect? And then finally, we can have a fixed length and a fixed mass, but release the pendulum from different angles. Does the angle of release affect the period of motion? And we're going to come up with a formula for period, and the period is not going to depend on the angle, but the formula we derive is going to come from simple harmonic motion, so it's only valid for small angles. So if you were to take this mass and hold it, horizontal and release it, it's going to make this very large amplitude motion, and what we're talking about here would not really apply. It's kind of interesting. How would we solve the correct equation with that sine of theta? And that's actually a very difficult thing to do. It doesn't have a nice solution where you could say like this is a nice solution. We're describing x, which is a function of time, and it's described by a cosine curve. So that's what we call a nice function. There's a certain set of solutions which we just consider nice because they're well known. But this general pendulum problem, it literally does not have a simple, nice solution we can write like this. Just putting that sine of theta makes things extremely complicated. But, so let's talk about the solution to simple harmonic motion when the small angle approximation is valid. So we're going to start out, we've got our equation. So exactly equal mathematically to a plus omega squared. X equals 0. So we can write theta as a function of time. Here, let's call this theta max times cosine omega t. Just like here, we have x equal to, we used a for amplitude, but here our amplitude would be an angle, so let's call that theta max. And it's described by a cosine function, just like, mass on a spring. But in this case, I erased it But remember, we had omega squared is equal to G over L. So again, this is on the equation sheet. There's only two examples of simple harmonic motion we're going to look at. One is a simple pendulum, and the other is a mass on a spring, which was K over M. So these are the only two we need to know. Those are on the equation sheet, so you don't need to even memorize those. But I cleaned the board today. Okay, so I can fix this. Now, we could talk about the angular velocity and acceleration as well, but it's kind of the same as before. We kind of run into an issue with notation, which is why I don't like going too far into this, because, you know, theta is angular position. Angular velocity, we use the letter omega, but we're already using that for angular frequency, and they're different because this is a constant, where the angular velocity is a function of time as well. Like when we release it, omega, or the angular velocity is 0. And then the angular velocity increases, reaches a maximum value, and then reaches 0 when it's at like minus that initial angle. So the notation gets a little problematic. But let's call this just like for angular velocity, that's how quickly the angle is changing with time. We could write that down as well. We're not going to really need that. And then alpha is a function of time. You know, we just basically the same as before. Just have to be a little careful with the notation because we don't want to use omega to mean two different things in the same equation. All right. Now, the reason I wrote these down, though, this is the angular velocity. We can see that the maximum angular velocity is going to be this angle times omega. So the amplitude, you know, measured in radians, times the this omega, the angular frequency. All right. So yeah, that's our solution. Let's talk about the period of motion now. So yeah, it's described by a cosine. So the period occurs after one cycle, which would mean, like, say we start out at t equals 0, theta is 0, and then when omega t equals 2 pi, we've completed a cycle. So just like before, omega times the period is 2 pi. And so the period is 2 pi over omega, or that would be 2 pi times the square root of L over G. So that'd be the period of motion for a simple pendulum. And we could break this into 4 pieces as well. If you find the period in seconds, say if you divide that by 4, that'd be the length of time from its maximum amplitude to 0, where theta equals 0. And then, again, that same time period to get to minus theta, and then an equal time period to get back, and then another one to get back to its starting place. So there's, you know, from maximum amplitude to 0, back to max amplitude and 0, and then back to the starting point. Those are like 4 equal periods of time. Okay. Now, that's it for this. We'll do an example in class of a pendulum problem. But I should point out one application of this. We can rewrite this equation. Let's square everything. So we have t squared equals 4 pi squared L over G. And we can rewrite this. We can say G equals 4 pi squared L over T squared. And what this simple pendulum is a way to measure the acceleration due to gravity. And it's a much more practical way than trying to drop something and analyze it, how quickly it's accelerating. We did that in lab, in the constant acceleration lab with the plastic fence with all the rectangles on it. But again, we needed a computer and a laser to do that, and an accurate clock. So not an easy thing to do, like what we did in the lab. It wasn't too hard for us because we have a computer that does most of the work for us. But yeah, just measuring the velocity at different times and kind of taking the slope of that. Not an easy thing to do without the equipment that we have. But making a pendulum, this is very simple. Just a mass on a string. And measuring the period, you just have it go back and forth and measure how long it takes to complete a cycle. You can do that with a stopwatch, and that's something we're going to do in the lab. Now, one thing, because there are significant errors in using a stopwatch, what we do to measure the period is we'd say let it go through 10 cycles, and then, divide by 10. And that would give us a more accurate way of measuring the period. And that works because provided that the initial angle is small, you notice that the period of motion depends on L and G, the length of the string, and gravity. It does not have any dependence on this angle. And so that allows us to calculate the period more accurately. If you did this pendulum and timed it for a while, you might notice the amplitude's decreasing because energy is being lost to friction, but that shouldn't affect the period. And that was actually a discovery that was made by Galileo. He was in church, and he was looking up, and just the chandelier was swaying back and forth in the wind. They had windows open back then. And he noticed when there's a gust of wind, the amplitude of the motion would increase, but he tried to measure as accurately as he could the period, and noticed that it did not seem to be affected by the amplitude. And that's true as long as the amplitude doesn't get too big. I guess Galileo used his own pulse as a clock. Not the most accurate thing, but it worked. All right, so we'll do an example of this in class, but one thing I want to talk about now is what if we don't have a simple pendulum? What if we have a different object other than just a mass tied to the end of a string? So let's look at that. We're going to keep this general. We're just going to have some mass. So it can be of any shape. Yeah, cleaning the board does not seem to do much good. Okay, so we have some object, some random shape, and I'm going to identify the center of mass because the torque on this object is going to be due to gravity, so we need to know where to put it. So we put in the center of mass. So this is our axis of rotation. And let's say the distance from the axis of rotation to the center of mass is r. And just like before, we're going to measure our angles with respect to the vertical. And so we have our line of force. This would be our lever arm. That's also angle. That angle is also theta. And so we can say our lever arm is r sine theta. So a little different, but basically we had L sine theta before. And again, that would work, this formula would work as well if we just did a mass on a string, because the center of mass would just be the location of the mass itself in that case. So we'd have big L sine theta. Okay, so let's apply Newton's second law just like before. So we start out, torque equals I alpha. So we have force times lever arm, that's minus mgr sine theta equals I alpha. Basically just going through the exact same thing we had before. Except before we had, ml squared. This time we're just leaving it general, just I. And now let's divide by I. Now, if we can say that that the small angle approximation is valid, then we have simple harmonic motion. mgr over I is a constant. So in general, for a general pendulum, omega squared would be mgr over I. And as a way to check that, let's go back to our simple mass on a string. Let's plug that in and see if we get G over L like before. So if we just have a mass on a string with a length L, let's plug that in our formula. We'd have omega squared is mg. And again, r was the distance from the axis of rotation to the center of mass. But again, all the mass is concentrated at one point. That would be the center of mass. So r is equal to L. And then the moment of inertia for a point particle is ml squared. And so we do get the exact same result we had before. So for a general pendulum, not just a mass on a string, we can always use this formula. So I want to look at an actual example of this. Let's say we take like a meter stick and have it free to oscillate around one end. So we'd like draw a hole in one end, stick something through that it can oscillate around, pull it through an angle, and just let it go. And so let's find the period of motion for this object. So first we need to know the moment of inertia of this object about its axis of rotation. And that would be 1/3 ml squared. So remember, about the center, the moment of inertia would be 1/12 ml squared. That's in the formula sheet, so you can look that up if you need to. That's rotating this mass about the center of mass. And we can use a parallel axis theorem, where the center of mass is just the midpoint. So that'd be this distance here is L over 2. So the moment about the end would be the moment about the center plus the total mass times that distance squared. And so we have ml squared, which we can factor out, and 1/12 plus 1/4. That's 1/12 plus 3/12, or 4/12, which is 1/3. So that gives us this result here. Okay, so let's plug things in. So omega squared, I mean mgr, where r is this distance from the axis of rotation to the center of mass. So that would be L over 2. And then we divide by the moment of inertia, which is 1/3 ml squared. So we have to clean this up a little bit. First, let's multiply the top and bottom by 6. So on top, we'll have 3 mgl. And on the bottom, we'll have 2 ml squared. And again, we get this partial cancellation. And basically, we have 3/2 times g over L. So this is before taking the square root. And so before, for a mass, concentrated at the end, we just had g over L. Now we're getting slightly higher value. All right. So yeah, I think that'll be it for pendulums. And yeah, we'll do some examples during the review. But I think we covered all the material. So that'll be it for now.